Okay, cool. Before we get started, I want to make a quick announcement. Right here behind Rohit's shiny head this is our website. So we're going to start recording these sessions and then posting them to our website. It's www.humana.io. And we'll also be sending out a link to these with every declension when it goes out from here on out. So for today, we have deck engineers Rohit, Wason, and Cody Hutchens to talk about machine learning part D, focusing on neural networks.
All right. Hello, I'm Cody Hutchens. This is Rohit. Yeah, Rohit X Wason. And how many of you, just out of curiosity, how many people came to the last machine learning one? Just to make sure you get an idea. All right. So in the last one, we talked a lot about machine learning and like maybe more from a conceptual basis. And we started with like a very simple linear regression program that was just very simple, very conceptual. And now we're going to kind of talk about more of like an application of it using like neural networks. Neural networks is a more powerful machine learning structure that exactly as it sounds will mimic the way we think that people think. So that being said, and just to let you know, so last time we had talked about what's called a distributive, distributive model. And then now we're going to be kind of touching on what the distributive model looks like in neural network and also what a generative model looks like.
Thanks, man. This mic might be a little shaky, so if people in the back can't hear me, let me know. So a quick recap from last time, it was about 3 weeks ago that we had met here. Like Cody mentioned, we talked about linear regression as a simple machine learning quote-unquote algorithm. And then we drew a picture here that had a bunch of dots, and all we were doing was drawing a line through the dots. And people who deal with numbers here, I see some of the faces here that do analytics for a living. They would agree that that's the simplest way of drawing a conclusion on questions like, are you an Android user or an iPhone user, and things like that. So those questions fall in the category of regression. We also talked about a healthcare-related question of, based on somebody's cancer screening results, because those results have numbers and images and other factors associated with them. Can we put them in the category of malignant versus benign? So that's it, like A versus B versus C, those kind of questions are regression-based questions. And linear regression is a great tool that we use for that. We showed a small, although relevant example for that. So that was one, and then we talked about image recognition of how Google does that today, and then if Google can recognize images of, let's say, trucks, somebody can extend that into, for example, recognizing food truck, or what kind of truck it is, what make or model that truck is. So you don't have to reinvent the wheel and go pixel by pixel again, like most programmers would think. So that's the beauty of machine learning algorithms. They are slowly becoming smarter and smarter, and then they render their smartness as reusable API, if you will. So you can build your little sliver of creativity on top of that, and then harness all the power of that you build.
And touch on that, like we talked about TensorFlow a little bit, if I'm not mistaken. We talked about TensorFlow, which is Google's, like, I guess you could call it. I would say more about an API for doing machine learning. It's actually really cool. But one of the things that it is trained on is something called inception. So they actually train like a baseline, I guess you could say, like baseline weights towards what images look like. Like, so if you're using TensorFlow, you get to utilize that. You get to utilize their data.
Yeah, nice. And then we talk about AI and ethics. There's definitely a debate going on there in terms of what is right, what's wrong. Should AIs be allowed to represent humans, and if so, in what capacity, and our interaction with machines. before we jump to today's presentation, I'd like to understand, at least from 2 or 3 of people in the audience, what is your goal with machine learning? Like, what do you, since most of you have seen the first presentation, where does that leave you in terms of unanswered questions? And I know engineers versus product people versus analysts will have all different interests. Anybody want to volunteer? I'll need at least 4 or 5 hands, and I'd like to hear your story of why are you here. Okay.
Yeah, I don't. The way I was trying to go about thinking about learning is, and I use the simplest example of sorting numbers, right? Where you have bubble sort that you use that's super simple, really easy to understand, really easy to get the machine to do it. But there's better ways of doing it. Would a machine be able to figure out better ways of doing a simple task like sorting when we have machine learning?
Good question. Thank you. Anybody else? And we want to do is we try to address some of these questions today. Yes.
So I think when we think a lot about the future of how we deliver care to our members, particularly through new, smarter, hyper-personalized care plans and care delivery models, we're going to have to be able to have these really complex, for lack of a better term, rules engines underneath those. And the cost of delivering these rules has to come down. The only way that you're going to reduce the cost of rules is if you can figure out ways for the rules to essentially write themselves. So the prohibitive cost of developing these rules engines in the future, we really need to have neural nets essentially in place to do that. So that's what I'm thinking.
That's a great question. It's probably a coincidence. Many people at Humana are talking about analytics and where to take it next, and some machine learning conversation also happening. And I was fortunate to be part of one of those conversations. There are some discussions. Maybe after the talk, I'd like to catch up with you and see, what kind of interest exists in Humana for that. Anybody else? Jason?
Yeah, like what are the steps between, understanding the concepts and moving towards something tangible? What are, because there's the dream and then there's the concept and there's this middle gap of what happens in between. It's what are some more of those concrete steps between concept and action?
So if you came up with an idea, let's say, that was a candidate for machine learning, how to go from concept to delivery, is that?
Yeah, what do steps of delivery look like? Like, when we talk about software we write today, we understand what it looks like. It's well understood in the industry what it looks like to take us a website from concept to delivery, similar to mobile apps. But it feels like there's a giant missing gap on machine learning type of things. Maybe they're so specialized in this one.
Right. Well, the quick answer is it is still under development, I think, as from what we have read. There are obviously job titles for machine learning engineers and machine learning analysts. Some of these consultants kind of play it by ear a little bit because the frameworks themselves are changing as we speak. So it will be kind of like what late 1990s was for web. People knew HTTP, but there was still a lot of things that were unknown. But we'll try to address that to some extent today. Sounds like that's about it. Cool. That's a recap. So we saw this hello world-ish problem, and Cody and I were hoping that we'll be able to demo this problem solved today. We ran into a bug. Something that we probably used last night, late last night. But what this is how can I recognize digits? And I won't spend too much time on this, but the picture explains itself that an image has 4 quarters, and these 4 quarters add to a 0. It's a pretty simple task.
And I just want to add that demo that Rohit was talking about. It was going to be a generative model, so we were going to take what we've learned, so we trained it on images, and we were going to actually have it produce an image, like a hand-drawn image by itself, without anybody actually doing anything. So that's kind of cool.
Cool. So a little under the hoods for that. So the term that Cody used is generated model. What is generated model? So this was presented last week. So what this is layers of neurons, if you will, that are connected to each other, and it doesn't have to be 3D or 2D. It could be any number that suits our problem. What happens is we are training this model on here are 100,000 images of digits, for example. for that simple example. And by the way, for a simple example like this, just to identify 10 digits of handwritten digits, you will need at least 50 to 100,000 images of handwritten samples to train on. That number seems daunting, but with 100 people in a room like this, I'm sure there are different handwriting and different patterns that we write. So it's only natural that we will need so much. And of course, more the sample data, the better your algorithm becomes. So that's needless to say. Every time you think machine learning, I'd like to leave you with an impression, think of your own brain. When we were younger, when we didn't recognize cursive at all, we're like, mommy, what is this? And this was A, right? And the reason she knew A because she had learned that, and now we have this cognition of this is another way of writing the letter A, was the cursive. And now we just became a little bit smarter. So that's what these neurons are doing in a digital way, that they're training themselves on images and say, oh, this is another way of writing an 8. Okay, I've learned that now. And the next time that same pattern is presented, it'll go 8 because it was reinforced in terms of its learning. So think of this picture as a bare bones picture. I'm going to talk through the picture. I don't have any cool animations to talk about. Was there a question?
Yeah.
Okay.
So your point about if it knows now that this is also an 8, and when it goes to evaluate 8s in the future, it takes that into consideration. Does the neural net kind of work against itself then, and the more it knows, the more it has to sift through to make that determination?
Yes and no. So you as the engineer or the designer of the neural net can make a decision that you're going to supply 55,000 images to this network, and then it will take, let's say, an hour to learn, and then you stop, and then you go, this is all you get to learn, kiddo, right? Unlike humans, because as humans we're constantly learning. Even right now we're learning things. I'm learning just by speaking. So, but you could make a decision saying you're never going to get any smarter than that. Versus, there are, let's say you run this thing and you project that to production like there are real life things happening to it. Let's say check processing at a bank. They've done that. Our check shows up that could not tell whether it was 8 or a 9 because it was written really. And that goes through a manual thing and the person says, okay, it's an 8. So that's a new learning, potentially, waiting to be digested in the system again. So as a designer, you could say, every night I'm going to get some outliers, let's say, 100 outliers every day, and I'm going to process them into the system again. Now, important thing there is with any machine learning or any AI-related technology, which, by the way, I think we presented AI versus machine learning last time. I don't think that was the intent. We kind of painted that black and white picture of AI versus B, and if you're AI, you're not machine learning. I don't think that was the intent. Maybe there was some discussion that happened in 3 weeks, and we have learned a little bit better since 3 weeks. Machine learning is among the consultants and the scientists. I think machine learning is seen as the most promising way of delivering AI. So it doesn't say that start thinking about AI, just think about machine learning. There's some terminology, obviously. And I think there was some negative connotation that AI had been painted with. Again, there's some movies and some pop culture examples, where like machines killing us. So I think people just wanted to change and get a new term out there. So hence the machine learning.
And
I think
right, we use the term traditional AI. So like what people thought traditionally of what AI
as a brute force way of traditional AI, which a simple, but the Google image search seems very simple now because it's being fed by millions, if not billions, of images, over the course of 10 to 20 years. The reason image search, and you can look for cute dogs and cute cat images online so easily because they didn't take the traditional AI approach where they would have to find the edges of the image and understand what a cat would look like. You can just imagine, just coming up with the word cat would take you years, to write that algorithm. So machine learning kind of cut and short-circuited that whole thing. Answer your question specifically, the outliers could be fed back to the system, to the same system. As a designer, I can make that decision. And now I'm slightly more knowledgeable about this. Cool. I'm going to use this as bare bones again. So if you can imagine, I wish I had time to draw animated, but if my input layer is fed from the left side, and in making iterations on that data, because all of that data is not fed all at once, That simple example of digit recognition had about 784 pixels that you could decide on. So if all those 784 pixels are fed on the left side and they travel left to right, what's happening is these lines are getting thinner or thicker. Now what does that mean? That's a direct analogy of the way neurons work in our own brains. When we say we learned something last time, I read an article, I learned something about art, for example. So what happened was I established newer and stronger bonds between the neurons in my mind without realizing that. I mean, that happens all the time, despite, again, like driving, talking, all of that. That is what learning is. So what scientists have been able to do is make these digital neurons sort of mimic the biological neurons and then make stronger or weaker bonds based on their learning. Why would I make a weaker bond? A weaker bond would be, for example, if, again, digits example, it says if I draw my 8 a certain way, and then people are telling me during the learning phase that this is like all the 8, right, because I wrote it, it's going to get stronger and stronger with that. Now, if it had a small doubt that this 8 could have been seen as a 6 or a 9, because that's true with some handwritings, it's going to make a weaker bond. It's going to say, in future, I'm going to probably predict that for like 5% of the cases, this could be a 6. 5% of the cases, this could be a 9. Because some of those examples could say that why it looks like an 8 is actually a 9. So a weaker bond is also worth making, so that you don't go that route as confidently as you would have in the other way. I hope those lines make sense. Any question?
Can I just question about how sort of analog versus digital that feedback loop is? Because it's not just about the processing of the information, right? It's getting the feedback. And I'm assuming that you can build the feedback, you can automate the feedback at the same time you can automate sort of the input, or is there a lot of manual required, probably, I guess, early on to enable that feedback loop?
So in most examples, the only manual intervention that's required is somebody designing this network.
Right.
And it's experimental. In most cases, it's experimental. There's no predefined picture. Like, I'm sure people who Google machine learning and find images, there's all kinds of these networks that show up, right? Some with 10 layers, some with 2 layers, and with different colors and all kind of patterns. To answer your question, there are 2 things that we see are manual intervention. One, definitely a programming effort. Somebody has to design this neural network. Which, by the way, for engineers in the room, it's getting easier and easier by the day. TensorFlow, TF-Learn, all these libraries that are being open source, only with the promise that making the entry point for machine learning easier and easier. I would say writing a machine learning algorithm or solution is far easier than making a mobile app. Mobile app is a lot more. Second part, that to answer your specific question, the manual intervention would be to label the training set. So in that digits again, somebody has to say that this is an 8 or a 9, or again a cat picture. Somebody has to have started with that decision that yes, this is a cat. This is what humans call cat. So the machine can say, okay, if I see features of an image like this, it's a cat. Other than that, there's no manual intervention, unless I'm not addressing your question.
Well, isn't that a little different between machine learning? Machine learning, which is really about, you actually kind of have to teach the machine to be able to do that, versus deep learning, the deep use of the neural nets, I think, isn't that much more of a self-learning environment?
It is. So that's a great point. I was going to bring up the term deep learning, but let's talk about it now. So machine learning, deep learning. Deep learning is just a subset of solutions that are from machine learning, like domain. There's a lot of terminology floating around these days, so it could be confusing. The reason we call deep learning deep is we just add more and more layers in between the input and output layer. So for those who were here last week or last time, Cody had written an example of if your first phone was iPhone and you've never had a problem with your phone, his theory was your current phone is an iPhone also, or something like that, right? Versus if your first phone was Android and if you had a problem with your phone, you probably switched to an iPhone. Yeah, there was like 2 or 3 different examples in that theory. So what we're doing there is we just have an input layer of what was your first phone, what do you own right, or did you have problems? And output would be you have an iPhone. Very simple example, right? The reason we throw these layers in between is if the nature of the question becomes complex. Image processing is
definitely an example of a complex thing, because I can't just upload a JPEG and say, is this a cat? Well, no, it's going to divide it among, like, if not pixel level, but on, you know, very small sections of pixels. And it's going to say, if it has these contours in the image, I'm going to treat this as a candidate, and let's move on to the next layer. The next layer is going to say, you told me yes, I'm going to look for the bigger question. Until you get to the end and it says, yes, it's a cat, or no, it's not a cat. So to answer your question, deep learning does feed back into itself. All these layers are not just moving from left to right. Data flows from left to right. The learning goes from right to left. In a mechanism that's called backpropagation. It's a mathematical concept, backpropagation. And until, I think last time we were presenting, I did not know the term. So I had to look it up and understand what that meant. What that really means is, in very simple terms, it is, if the image says it's an 8, let me run through my notes and my links and then find out what I think it is. If I think it's a 5, I'm going to negate all the choices that I have made. I'm going to make those bonds weaker and weaker. So I never say 5 again for this image, because everyone's telling me that it's an 8, right? Let me try this again. Oh, it's a 6. No, it's not a 6, because they're telling me it's an 8. Until I get an 8. And when I get an 8, I'm going to solidify those links and say, that's a thumbs up for me. Human told me 8, and I got an 8. So, you know, they were teaching me something and I learned it, right? And that is called reinforcement also, because more and more 8s show up and I keep getting better and better answer. Those bonds, again, those lines, keep getting thicker and thicker, and other lines become thinner. Okay? So by the end of the 55,000 image, what I have done is, hopefully, if there was enough randomness in the data and I didn't just give zeros in all the images, I would have drawn these lines into a thickness that is more conducive to any real life problem. So now you shoot an image at me, I'll probably be able to tell within some percentage of confidence whether it's 0 or 1 or 2, 9. Again, we're using simple examples like that. Switch to cancer screening, a problem that is relevant to healthcare today and, you know, humankind in general. If I can look at the mammogram image of a breast cancer suspect, and I can look at various aspects of that result, maybe thickness and size and colors, and there are at least, I think we found an example where we have 32 different attributes to a cancer screening. It could be more. Now, if you look at these 32 attributes, and we can train ourselves, the doctor's results, you know, out of these, let's say, 50,000 input examples, can tell us that these scans were malignant and these were not. Because the human's telling me, teaching me something. And again, run the same example of digit scale, like I said. These bonds will become stronger or weaker one way or the other, and by the end of it, hopefully I can send you an image, upload an image, and this algorithm can detect malignant. That answer your question?
Just to add on to that, I think learning also can happen through having neural networks like challenge each other. So, like in AlphaGo example, when DeepMind did AlphaGo, it essentially had both itself, it played itself 30 million times, and that's how it learned. By the way, that was the fastest way to learn. So they kind of automated that learning process. Yeah, exactly.
Simon.
The learning at the end of the day, I'm looking at a neural net, like an engineer brain multiplied graph, right? So at the end of the day, what we're basically saying is those paths of back propagation, those are just collecting the vectors through the graph, and then at the end of the day, that vector has a thickness.
It's got a width or weight on it.
Right.
Exactly.
Okay, so that the actual learning is actually kept in basically collecting a vector that has a
Exactly.
value of number, weight associated.
Exactly. Which is why you will see that most AI or machine learning startups are not selling their algorithms. They're selling their models.
Right.
Or selling that's their proprietary system. They're using all the open source algorithm, open source code for doing this. But really the true value that we bring to the table is the thicknesses of these lines. And there's another element called the biases, which is sort of a secondary concept, but it's important also. In math, you know, you do some integration and you add a constant. So think of biases as constant. So really, if we boil it down, the true value of machine learning that is proprietary would be how thick are these lines and what are the biases in these lines. So yes, that's a good point. It's a graph. Image recognition and image processing. People use Prisma. I love this app. only if I can get my good pictures on. You use your picture and you use Van Gogh's actual painting, and then basically you marry them up, and there you go. There you have the Prisma-fied image. Prisma actually, Cody looked it up. Prisma markets itself as an AI company. They're not an image processing company. They're not just another Instagram. They're an AI company. And truly so, because this is what they're doing. So their algorithm has learned what a Van Gogh image looks like, a Van Gogh painting would look like. And you can basically Van Goghify any image that you upload. Anybody what artist is this? It's Picasso. I didn't know either. All right, Human Genome Project. We've all heard of this. They say they have cracked all the genes and all the chromosomes in our genes to the last detail. Yes and no. They have identified these chromosomes. And a scientist did a TED talk. His name's going to pop up here because it's escaping me right now. And he brought, he had printed for the first time in history, I think it was about 22 million pages, like the printed A4 standard sheets of paper with just A, C, G, and whatever that fourth one is. T, thank you. All the chromosomes. So all the combinations of these only 4 letters are printed on 24 million sheets of paper to represent one human being. So everything about that person is being identified. So that's what has happened. What has not happened is we haven't tapped into about 98% of these chromosomes to do anything with. We haven't really found an application to say how do we inject in these chromosomes, or maybe alter them, or maybe understand a little better how their lifestyle could be changed, or their health could be changed, or well-being could be changed. So Genome Project is awesome. The application of it is still underway, but it's progressing thanks to AI and machine learning, because the stuff that used to take years to process, again, with the simple algorithm that I just described about digit recognition, imagine, you can throw any number at that, in that combination of neural net, and end of the day, it's all numbers anyway, so it can process and find results. What kind of results? So that's just an image of, like I said, we get your genomes. Yeah, this is really interesting. So if we get your genomes using the Genome Project, and we get all those 22 million pages worth of data, and we get your biometrics, for example, or your habit pattern, or how are you feeling on a general basis, or your history of how you've been feeling. Let's say I had a surgery 5 years ago, I'm feeling better now. So everything about me from the outside is on the right side, and everything about me from the inside is on the left side. We made these two up. What we now have is we can identify to a precision of between 85 and 90% your gender, height, age, eye color, skin tone, many other things, including your face. So the TED Talk, for those who haven't seen, really impressive. I'll share a link, or you can Google. The scientist's name is Riccardo Sabatini. He's in San Francisco area, owns a startup company. And so you might ask, what does it do for me? If you can recognize my face, fine, that's impressive for like 2 seconds, but then what? Crime scene profiling. So imagine, saliva samples, or blood samples, or other traces the criminals leave at the scene. People do that for recognized crime profiling, like if someone has seen anybody. In this case, you don't have to see anything. You just have to get a trace of their hair, and then pretty much paint a face like this. What you're looking at is, on the left side is the actual subject's picture, and on the right side is the generated image of their face. I won't say this is 100% accurate, but pretty close. If I show the image on the right side and this person happens to be a criminal, I would be worried if it was me. We're a healthcare company, we're a wellness company. It's always important, like some examples out there, you've asked about how can we make it cheaper and better and more accessible to our patients and members' lives better. Imagine with the Genome Project again, if we can, with the Genome Project, we're not looking at your history or your father's history, we're looking at all your history, from the beginning of time in a way. And then if we can decide what kind of ailments you're going to have, and not only that, that we design your treatment for you. So think of buying and going to Walgreens and then getting a pill or a bottle of pills designed for you. It's customized for me because my genes have been shared and all my inside out has been talked about and analyzed on the greatest degree. That doesn't happen today. That's why we have side effects. That's why we have drug-to-drug interactions. Imagine taking one pill for all your problems, and that's customized to you. That would be a big win. I think there's expecting again that TED Talk I think predicts in the next 10 to 15 years we should be there. So Omkar, your question about algorithms. Before I go too far into healthcare, I think algorithms are also success-based scenario, in the sense that bubble sort or sort, I gave you an unsorted list. My success criteria is did you succeed or not. There's no two way. The list is either sorted or not, right? So by anything that can be put a 1 or 0 on the success or failure can be fed through the neural network. So to answer your question, I think in theory yes, and maybe in practice somebody is doing it already. You can write. You can design a
success is efficiency, processing times.
Sure, yeah, so add more factors to success. Not only, that's a good point, not only am I talking about have I sorted the list, but how much time did I spend on it? CPU cycles maybe, or other aspects of it too. So all of that could be success, and then machines can, in theory again, I haven't seen an example like that, but you can make random, non-performant, weird-looking algorithms first and say it's not even sorted, just get rid of it. Or tap into some predefined repository of algorithms, maybe GitHub, all the open source programs that are out there, and then see if anything looks like sort-ish, and then run that, and then train yourself on what is working and what is not working, right? That problem is definitely more complex than identifying digits, or even identifying like cancer results, because these are number-based things. You have 32 inputs and you have 1 output. But I think in theory that's definitely possible. OpenAI was started last year. Elon Musk and his friends own that company, or his open source project rather. One of their challenges that is out there for engineers is writing an AI program that can go and win program writing competitions. So we always have contests, right? Like in crowdsourcing board, we always have write an algorithm and we'll see if we want to pay you or not. So one of the open challenges out there is somewhere on those lines of writing algorithms. Pretty cool. All in all, I think what we've talked about now is we've looked at some image and some other interesting looking like game playing, like Cody mentioned. AlphaGo beat itself 30 million times and then learned something in the end. But then so what? So what if we are able to play Atari games from the 80s and or 90s or whatever? I'm not a gamer.
So just to make that clear, they took the same algorithm and put it to a new game and it completely destroyed. Like it played that ball game where it hits all the breaks all the little things and bounces back up. This thing is like, yeah, it was crazy. Like the same algorithm that drove AlphaGo was doing this. So
that's a good point. So if these algorithms are written and if we are patting ourselves on the back saying we beat a human in AlphaGo, I think the so what in there lies in the fact that the same algorithm could be subjected to a real human problem. Sorry, gamers, games is not a real problem. Like healthcare, wellness, relationships. eHarmony and all those things that say they claim the 23-point match, right? Imagine machine learning being at play there. And I'm not even kidding. I think it's definitely a very good use case if that's not already happening. Of saying that you in relationships haven't worked out with these 10 kind of people. Don't even go there. But in all seriousness, I think healthcare happens to be definitely a focus here. World hunger, avoiding wars, avoiding conflict. I think machine learning can definitely be applied to all these areas. And to Cody's point, once you write this algorithm and once you spend this kind of energy in one problem like AlphaGo or gaming, it can be very easily tweaked into processing numbers, because at the end of the day, they're all numbers. Whether my image has this quarter with an angle on it or not, because I'm trying to deduce a zero out of it, versus whether there's a, in the news feed from Syria, whether there's some keywords present, and that means something might be heating up. End of the day, it's all numbers. So the same algorithms could be trained with little effort to process some more meaningful and humane causes. That's really all we have to show in terms of slide. We have 2 programs in flight. Hopefully there'll be a 3rd part soon. And the cancer example that I keep talking about may get some traction. I think we're just doing it on our own. We don't have real examples, but we have about 500, 600 examples that we downloaded from an open source website somewhere that we'll be able to, hopefully we will share with you guys. If it happens before the 3rd time we meet and we have something to demonstrate, we will probably send code base to Sarah for people to look at. I'm going to open the floor. I don't know what time it is, but we can open the floor for discussion or any questions that may have generated.
What happens if you feed it bad data, like the check reading example? What if the teller can't actually read the digit, but they are able to look up some additional information of the?
What happens when people use bad words on kids? Same thing. So you feed it with bad data, it will learn something bad about it, and it will keep saying, oh, it's an 8, where it's a 5 because you told it it was an 8. Now, how consistent you are with the bad data is important. And I think we talked about ethics last time. We touched upon this. I'm sure it's a subject for another day. I'm not knowledgeable enough in the subject of ethics, but well, AI and ethics. Pretty ethical myself. Just finished my training. I'm proof. So real quick there. So I think the question of ethics was because it's a stereotype, because most programmers in the world are males of a certain age, maybe of certain demographics. Are these programmers, AI programmers, unknowingly creating biases in the AI systems that is AI becoming a male of a certain demographic from a certain part of the world? We don't know that answer, but I think that's a question worth asking. So that's a bigger question, but I think to address that specific question, if you provide bad data, garbage in, garbage out.
And also, I think Rohit, where he said it depends on the volume, right? So if you have like a ton of bad data, like over and over and over again, yeah, it's going to really affect it. But if you have like a one-off, like one time, but then other data kind of balances it out, it'll be great. Then you get the bad data, you get what happened to Microsoft and its Twitter AI,
Good example.
Yeah.
Jason, any question?
Yeah, I was just gonna say, wouldn't back propagation kind of prevent those one-offs from being a problem?
The one-offs it will, yes.
Okay.
It'll say most of the time you told me it's an 8, now you're telling me it's 5. I'm going to believe for most of the time.
Because most systems aren't just gonna take that at face value, they're gonna run it through and say, what do I think you are? Do I need to take you into account or discard you? You're not running anything new from this.
Exactly, yeah. I mean, all of it depends on, if you answer the previous question that we answered, is on that human effort of supplying the right kind of training data is the biggest thing. Algorithms, frameworks, all these cool examples are fine, but for a real problem like healthcare wellness, if our data is flawed, or we just misread the data, we just misinterpreted the data, then we're going to have some flaws in the output. What's the question?
That's what I was going to ask.
Okay, cool.
It's a nice term to describe that as revising your belief in one direction or another based on your input data. If your input data is bad, and you get one piece of it that's bad, you'll revise your belief in the wrong direction just a little bit. But it's kind of balanced by most of the data is good.
Good point.
Has there been any research into how the speed of learning improve depending on the data that you're giving it? So an example being like, okay, I'm going to feed it 100 different types of zeros, so then when I try to teach it to know what 2 is, it'll more easily determine that as opposed to like trying to set a bunch of random numbers and try and teach you all at once.
So I haven't seen an example where the size of input data changes the speed. What I did come across, this one professor from Toronto University, Jeffrey, forget his last name. He had a talk, and then he was talking about, I think he's considered the modern father of deep learning because he came up with this idea of introducing many layers and not just stopping at input and output. Because traditional regression analytics is input and output, maybe just one other layer for some conditional branching. They've been adding many layers, and he wasn't sure why. Because what happened was he went on vacation, and I think his substitute professors or his students, one or the other, decided to just randomly add new layers. You know, what happened was when they added new layers, the performance just shot up. It became really, really fast. So I hate to say this, but kind of like brain, I think there are some unknowns in AI and machine learning. Even with the things we have achieved, some of them are hard to explain or impossible right now to explain why we've been able to achieve those things. But again, it's kind of like brain because the moment your complexity starts becoming many to many, and that picture was only like 20 nodes, but when we're talking about millions of nodes, the complexity is just so hard to explain that it's almost like quantum-like performance. That's the analogy I have in my mind. But I don't think it's magic, obviously, because some people just jokingly say it's just magic. But I think something we haven't been able to explain yet. But to answer your question, I think you add more layers for performance gain.
This is sort of a meta question, so I apologize, but there's, I'm understanding how this can sort of lay out better information. But the next step on that is decision making, like self-driving cars and all the ethics that are involved in trying to move from just providing better predictive information as opposed to the actual decision making, judgment, emotion, and so on. Those that is involved in that, but human is involved. Some of that makes decision making messier. So what is the sort of school of thought, sort of meta school of thought about how far this level of sort of learning and information can go into sort of decision making?
The only thing I've come across is Google has deliberately made a red button that we will be able to turn off. What that means is, I think their way of telling the world that if we go too far, here's a red button. And I don't know if it's Google owns the red button, they fall down and press it, but I'm hoping that consortiums like OpenAI and Elon Musk personally is very interested in that whole space.
I'm thinking just even in healthcare, like there's a lot of decisions in healthcare that actually may be better made by a machine learning sort of neural networks or algorithms. And there are others where you're going to need to factor in a lot of sort of emotional components to it that the machine may actually over time will be able to actually learn those emotional components as well.
One thing I'd like to add, I'd like to throw a different light on that question is, in my mind, emotions are also controlled by neurons. So emotions are also learnings that seem a little soft because we apply emotions on certain softer subjects in life than others. But I think at the end of the day, emotions are also neurons and weights based on what makes me feel better or not. So maybe it won't be impossible or too much of a stretch to say that an algorithm could be written to mimic human emotions, like specific to one.
Right, you can read face and apply emotional content to faces now, so you can start to use that as inputs.
Well, that's the reverse side of it. That is me deciding what emotions you want to convey based on your face, right? But I thought your question was more about can I make this decision with a bit of an emotion in it?
Right.
And I think the answer is yes to that one.
So, okay, so just to go back to that question though, my understanding was that you were saying, how can we make decisions based on the machine? Or like, can the machine itself make the decision in place of the person?
Well, I think, we are going to use these as decision-making tools.
Right,
The question, right? So the question is to what degree there's going to be human intervention to ensure,
Okay.
that this is the right decision. But in some cases, certainly, machines are making decisions all the time, and they build cars, right? So at what point when we're in healthcare, where there's life or death kind of decisions, I'm asking more of sort of the ethical conversations that are happening about where's the edge?
And it seems like, just from the conversations we've had, would be like, it would maybe understand what the best thing to do would be and make a recommendation to that person. So like I think of an example would be like a doctor prescribing medication, right? A lot of times I feel like they might be influenced by salespeople or some other cases that, you know, I'm just gonna prescribe you this for like whatever the case is. But what if we could actually get behind that and say make a data-driven suggestion to the physician saying like, oh, we've seen with managing diabetes, this combination of medication works the best. So here you go, what do you think about that? And then like let them say, oh, okay, we're gonna go with that, or no, we're not gonna go with
So
that.
I'm going further than that, right? My brain is going to surgery. We're in the middle of surgery, and there is a machine that's actually conducting the surgery. And at some point, something goes wrong.
Right.
The doctor thinks one thing should happen, the machine is saying another thing. Who owns that decision? How do you manage that? It's not unlike self-driving cars right now. Who's making those hard decisions when you gotta slam on the brakes? So who owns that? Who owns that decision? Who owns
That's a great
responsible?
question. Yeah.
Yeah, absolutely.
I don't know if I've read enough about ethics like that. I think it definitely falls in the bracket of ethics.
Yeah.
The other thing to also think about, which puts a meta on this meta, is
Yeah.
even if we do make our machines ethical, who's training to make this ethics?
Right.
It's us. So they're only going to be as ethical as we are. So I mean, it just starts getting gnarly and gnarly the more you think about it. I'm a big fan of the movie Her and Ex Machina, both of them in that order, by the way, if you haven't watched them. And I met an AI professor who teaches at UK, and seems very knowledgeable about AI, but I was like a kid. I was like, oh, this movie, have you seen it? She was like, hate that, because it doesn't address the question of ethics at all. Like, you know, machines falling in love with the person. Spoiler, but question.
I think going to your point, I think the ultimate determination is who sets the legal precedent. Like, there isn't one yet, but as soon as it goes to the Supreme Court, no one's decided it's either the human or the machine yet, but eventually.
But I think I mean, you go to the Cleveland Clinic, and they do have robots doing surgery. But there's a surgeon in the room, the red room. And I have a question, I'm assuming, and this is like way out of line, but the concept of neural networks and Wason, so there's some conversation going on now about using that technology in our call centers. And when I think about emotion, you could have two people calling the same question, but one person is calm and the other one is upset. You know, what happens then? And how do you train it to say, this should be escalated to a human being? Don't have that thought continue to talk back to this person because they need human contact.
We just heard this today. There was, I think there's already a pilot in Humana already using
I
concept
haven't
like
seen.
tone-based
Yeah.
switching and context switching.
And Gio does that thing, you recognize what tone of voice.
Yeah.
Your point is really interesting because we've kind of been talking about the actor in this, the person what they make the decision, but the person being acted upon is not really discussed. So where does that degree of complexity come in? That sort of situation makes sense. Also, like end of life care. Maybe there is one person who wants to, go to like all the way to the end, like keep me alive as long as possible. Another person just wants to like die peacefully in the bed. That I think to me is like where it gets really difficult solving healthcare.
Just had this image in my mind while you guys were talking is, you know, how we've seen the story of Watson beating human in Jeopardy and, you know, AlphaGo beating human in a game. Maybe the next big story will be like Watson winning a case in court. It's highly unethical to think that because court systems are for humans and made by humans and for humans. Maybe that puts a question at some point is what is it to be human?
Right.
Can a machine made out of steel and powered by electricity be a human?
Kind of along that, sorry, you wrote the work that you had. To that example, what role does, if any, does motivation play in machine learning? Can a machine know, like, oh, I'm defending this client, or does it play a better role as like a judge based on laws and facts?
would think that it would use previous court cases. So it would, I think the best way it would work in that is say, based on the previous, verdicts on these assumptions, they were guilty, not guilty, or whatever the case would be. So like, I think. Yeah.
And sort of along those lines, so Google, the example of like Google self-driving cars, learning to minimize fatalities. So there's an example that I've read where a mom and her child are in a car that they bought and it's driving them to school or whatever, and then another mom and her child and a dog walk across the street. The car has to decide, do I hit and kill this mom and child and dog, or do I avoid this mom and child and dog to save them? In doing that,
At the expense of the
kill my passengers.
The answer
So, like,
is,
the
you
difference
get the
is-
lawyer on the sidebar. That's what it is.
So the difference is just like the dog, right? But then you have this other variable of like passengers paid for the car. Should that matter? Like, I don't know.
Can I also, there's another article that I read about that, which is that because of the speed of the processing that can take place, is that we look at these as black and white issues, like I will hit this and this one will die and this one won't. But a machine can actually process the probabilistic nature underneath each of those and make a decision much more finely tuned than we could in that kind of amount of time. So that what they're saying is that actually if you do machine learning in those like moments where we see it as life or death, actually the machine can make a decision about what is the best course of action that will lead to the greatest saving of life, as opposed to because they can look at the probabilities against each of those things real time and fast. So it's more than
You could see what humans won't be able to see in
you see
the
and
time.
process in that amount of time that a human would not be able to do.
Like to slow down before you hit the wall. And nobody does.
Yes, nobody does. Yeah, there might be injuries, but they can figure out the highest likelihood of saving the most.
I guess my question was more around like if the highest likelihood of if like saving the most life or injury or whatever, if that decision doesn't benefit its owner. So like should it benefit its owner? They pay for the car, or should it benefit everyone? Like
Really good versus
right.
That's a really scary question. I actually don't think I answered the question.
Yeah, exactly. It's an ethical thing, but if it's like something I don't know is making a decision.
Sounds like we have enough interest in AI in ethics. Maybe we should have, like we did once, we had a rotation of some speakers and then people from the audience also rotated with them. Maybe we should do one of those.
Yeah, that'd be
Because
really
you all are great speakers. I'm liking this. But we're out of time, unfortunately. If you have questions, you can email to us.